Okay, well, welcome. Today I'm going to talk about modeling complex relations. So I've now seen many times where people have this idea to start using a graph database, and then they have these entities that they want to connect directly, and somehow people start by thinking, okay, let's just model the relationship between these objects directly with a graph, and then let's hang all the attribute values on the edge. But what we've seen is that sometimes that just gets too complicated. So in many use cases, we now see that it might be much better to put a relationship object between objects. So replace the complex relationship between with a relationship object. And then what we've seen is that actually you want to use both at the same time. So I'm going to just discuss a few use cases and see the modeling choices that we had to make. Yeah. So again, say you are a company that tries to find fraud, and you're a tax organization, or you're trying to find fraud, and it's very important to look at all the ways that a person or two companies can be related. And one thing that might show a relationship is that companies have the same address. However, that address can be in itself a very complex thing, because people just might have shared the address over different time periods. Yeah. So how do you model it? Or you might work for an online bank and you want to express that person one paid person two. But the paid relationship can be a complex thing in itself, because there's an amount, there's a place where something was paid. And so again, that turns quickly into a complex relationship. You might have, we did some work with an investment bank, and they wanted to use CrunchBase to do analytics. And so they wanted to see the relationship of who invested in who acquired whom. And their first instinct and the first idea was, okay, we'll take the relationship between an investor and a company, and we use the invested in relationship. But pretty quickly we found out that you have investment rounds where multiple investors would all go in the same round and then invest in a particular company. So again, the investor relationship was too complex. And I'm also going to talk today about something we do in healthcare, where we have about 2.7 million patients, 10 years of medical records, and say you want to compute the chance that you will get dermatitis, given that you have asthma. Well, the first idea is, again, okay, let's just have a link correlated with, but then there's so many things you want to say about correlated with that it gets too complex and you need something else. So yes, in many cases you can use a property graph and it will almost work, yeah, because of course you can put attribute values on the edges or on the links between two nodes. But unfortunately, in a regular property graph database, the values cannot be nodes themselves. So if your edge has attributes that are in themselves very complicated, then it just doesn't work to use the property graph approach. The other thing is, if you want to visualize, so in the 4 use cases that I'm going to show you, I'll talk about a little bit, it's every time an application that's for analysts, and the analysts want to look at the complex relationship and see more meta information about it. So if you just use the property graph approach, it's very hard to look at all the properties of your edge. So that's a problem with the property graph approach. And then finally, you want your queries to be fast, and the attribute value approach on property graphs isn't as integrated in a query optimizer as you really would like to. So again, these are all arguments to use a relationship object in the middle. So the pattern that I'm going to talk about today is where we, instead of having a direct edge between two nodes, we use a relationship object. But then for super fast graph algorithms, we also keep the original link around. Yeah. So this is not in any way big new technology. This is just a pattern that we've seen that works. And I'm just going to take you through a few use cases. So one use case was for an online bank where our client said, well, I want to use a direct link. Yeah, they were even using the GML to read in relationship to read in the transactions between people that paid. And they wanted to see the direct links, but then they also wanted to see all the meta information about the links. And the meta information in itself got complex because, say, someone does a payment from a particular place and that place has attributes, then how do you do a query where you also take into account the metadata about the place where you did the payment? So that was the first time we said, okay, well, just let's not make it too complicated. Let's put object in the middle. So here you see a person, Bruce, that made a payment to this particular person. And this person made a payment to her. She made and a payment to her, and then she paid this person. Oh, sorry, paid this person. Yeah, but again, it doesn't say much. So if you just replace these edges with objects, it becomes suddenly much clearer. Yeah. Oh, by the way, so look at this one here. So we see Bruce and Loretta again that we saw in the previous slide. But now we see that the payment was $111. We see the exact date when the payment was made, and we say the place where the payment was made. By the way, for people familiar with Semantic Graph Databases, these are just labels. But in the newest graph, we'll also make it possible that you specify like a dynamic labels for every object, so you can specify what attributes you want to see when you look at a particular object. Yeah, but just to give it here, so what we had was this, yeah, simple relationship, hard to see anything about the when, what, and how much, and here the objects in the middle. And then what I want to say about attributes having values, well, if you use the object in the middle, then here you can show that these two payments here were actually both made from Santa Rosa, yeah, and then you can have all the other properties like the latitude and the longitude and the population and the place where the payment was made. So this is one use case where it was much better to have a complex object in the middle, sorry, a relationship object in the middle. But if you wanted to do fast graph search, you still can use the original relationship. So here you see going from Bruce to this person here, and here we use the direct relationship without the information. So the graph algorithms will work much faster. By the way, what we did also for the customer is actually color code the edges based on the size of the transaction, so you still can put more information. And if we wanted to, we could even make these lines thicker or thinner based on the amount. Yeah. So this is the first little use case where instead of using only direct links and property graphs, we used a complex object in the middle. Then the second use case we did for a European tax office, where they were looking for many types of fraud, but mostly shell games. I hope that most people in the audience know what a shell game is. It's usually about a person that controls a company that owns other companies, that owns other companies, that owns other companies. Yeah, and then in the end, the lowest level company does something bad, like buying 100 cars that instantly go out of business. The company above goes out of business. The company above goes out of business. And then the tax doesn't have anyone to go to, but also the creditors don't have anyone to go to. Yeah? And this happens a lot. Yeah? So they wanted an application where they would make it much easier to find these interconnections between companies. Now, this was the shell games, but there's many other things. So actually, there's a beautiful document, I think from Harvard, with 200 ways, 200 most popular ways to do tax fraud. About 100 of them you can only discover if you can discover a relationship between companies. Yeah. So in all these cases, it's always important to be able to find relationship between people and companies. And for this demo that we show you here, which is actually used for real in production, you have data from all the local chambers of commerce. And for the demo I give you, I'll only have the data from the Chamber of Commerce because that's public information. The tax organization themselves has many, many more types of information, as you can imagine. Yeah, and then within that data set, we have about 5 million legal entities. Yeah, about 3.2 million of them are human entities, and the rest are all other types of entities. I'm not even going through them, but you can imagine that you might have a foreign limited or a government institute or a European cooperative LLC, etc., etc. Yeah, so many types of of companies. And then there are relationships between these legal entities. Now, doing a direct link between them is something that you could do, but the problem is there's actually bitemporal relationships between, say, legal entities. Because as a person, you might be an executive for a company from a start time to an end time, recorded at a particular time, or a company might own another company from a start time to an end time and recorded at a certain time. Yeah. And you might have a particular role relationship between them. So a direct relationship is possible, but it was much better to have like a role relationship in the middle. Yeah. And so here is a graph picture, and graph is our tool, our visualization tool on top of AllegroGraph, where you see that a particular person, Dharmendra, was an executive from 12/9/2011 to 1/6/2013 for this particular foundation. The green line says performs role, and think of performs role as the active part in the relationship and has role as the passive part. Yeah? So Dharmendra was an executive for this foundation. Then this foundation was a stock owner from this date to this date for this particular holding company, and then this holding company was a stock owner from this date to this date for this particular company, etc., etc. We've seen this pattern almost 9 levels deep, companies owning other companies. You can imagine if you're 9 levels deep and the 5 layers above go bankrupt, that no one in the world will be able to figure out who's has to pay tax at some level. Anyway, so this is, I hope you understand, this is one way. Again, I could have had a direct line between them, but it was for the analyst far better to have an object in the middle that he could inspect. Yeah. So I said we talked about the shell game. So this is how they use this. So say you start with a particular person. What you're really interested in is a person that is in control of a company that then owns another company, which owns another company. Yeah. So here is what we call a visual sparkle query. So in our graph, you can actually build up this query automatically, and then you can run the query as sparkle as problem. Actually, why don't I just show this? Yeah. So I go to the query view. I actually have the query, I think, already here. Yeah. And I can run the query. And here you see the sparkle query that was automatically created. Yeah. And then here you see the visual graph. Now this was actually the problem that this text service ran into, is they could do queries like this in their relational database, but then they got a table like this, and this, of course, I mean, how can any human being see a graph in this? So anyway, so you can just create the visual graph out of the sparkle query. And now you see the pattern. Now you see the relationship. Now this might be still a little bit confusing. So let's take, where's Dharmendra, the start person that I was looking for? Oh yeah, let's take this person and let me do a tree layout. Yeah. So now you see a much better representation of the same relationship, and you see this person being the executive for various companies, and then each of these companies owns other companies that own other companies. Let me take this thing out and do it again. So I took out the type. Oh, it didn't change it much. Yeah. So this is how this was used with these complex relationship objects, these role objects in the middle. Going back to my presentation. I did this already. Now, of course, there are many other relationships. Yeah. For example, two companies might not have a role relationship, but they might be at the same address, which is more like a weak link, because yes, there's a lot of big buildings in this world that house multiple companies. And of course, you have a much better relationship that if some person, yeah, or the company itself shared an email address at a certain time, or a telephone, yeah, then it becomes already a little bit more personal, and there might be a connection. And so what we have there is again a bidirectional relationship where we can say that someone shared an email, yeah, but for each, say looking at an email, we look at the start time that you had the email, at the end time, and we recorded when we knew about the start time and the end time, so that you can do bitemporal queries on this. Let me give an example. So say we know there's a weak link between this particular foundation and this foundation. Yeah. But let's look at it in more detail. In this case, this foundation had an address time frame from 1/1/2013 to 12/8/2013. I'm doing this in the European way, by the way. And they were all at this particular address. And then this company was from 13/12/2013. There's probably not even overlapping. It is overlapping. Anyway, I hope you probably get the point. Yeah. So saying that people have the same address is actually very complicated, and we needed even 3 objects in the middle instead of just a direct link. Now, every time when we do this with clients, or when the clients think about it themselves, is that, oh wow, but this will make graph search very slow if we have to do social network analytics, or if we want to do shortest path, say having the same telephone numbers and emails, you get really, really deep with great branching factors. So we came up with the concept of the super graph or the summary graph, yeah, where we will have a complex relationship up to in the middle, but we also replace it with the direct link. Yeah? So instead of starting with the direct link, we do it only after the fact. Yeah, we always start with the complex relationships in the middle, but if we need to, we summarize it with a single edge. Yeah, and so now you can do very fast search, and then once you find a relationship, then we rehydrate that link with the original relationship object, so that an analyst again can look at it and have more detail. Now, I'm going to, well, let me show you here. Yeah, so for example, here is the relationship that I showed you earlier, this guy being an executive for this foundation, all the way going down to class, which was a bookkeeper here. What we do is we just bypass in between objects, and we create just a direct link. Yeah, we call it a strong link because role relations probably are very strong. If 2 companies are related through people, it's probably pretty strong that there is a real link between these companies. So, yeah, so here's the original thing on the right, what you see on the left, but as you can see, you can bypass it here. Same thing for the weak relationship. Say you want to find a relationship between this person and this company, and then you can go through a telephone number and an address, and you also can find that somehow these might be weakly connected. And again, what we've done, write some easy code to bypass all these things, all these objects here with direct links. We call them weak links. And by the way, the supergraph sounds very complicated and like huge new big technology, but actually it's just very simple SPARQL queries. Yeah, so you can, for strong links, you would do the very simple SPARQL query where you say P1 is a strong link to P2 if they're role objects where one is the active part, well, one is the active and one is the passive one. Yeah, so this is simple. It gets a little bit more complicated when we have, say, a connection through emails, because we'll find so many links that we actually embedded this in a little list fragment, or we could do the same thing in a JavaScript fragment where we do the SPARQL query, and then we say add a triple if not exist, because otherwise we get too many duplicates. And then entity has a weak link to entity 2. And we make sure that the 4th element is inferred, a flag inferred, so if we want to delete it later, we can just throw it away. So the dehydration is obviously not that complicated too. So say we start, let me do the demo again. Let me throw this all away. Let's say we want to find the relationship between this person, Dharmendra, and this bookkeeper. Yeah. Now I could use a strong, the strong relationship. So what I do is I select strong link. Yeah. So what I've done when I do this, SP, and then I choose, say, the strong link. Basically, what I do is I generate an object that we call a generator. And what the generator is that it's a function that takes as an input a node and will, as an output, produce all the children of that node based on the predicate that I selected. And in this case, when we do it in graph, it's bidirectional. It will go in both directions. When you do this in a programming language, JavaScript or Lisp, then you actually can specify when you want to do a unidirectional or bidirectional search. So I could look at this, yeah, and try to find the shortest path using the strong links, and I find that I can get from Dharmendra to class through two intermediate objects. I can go back, do this again, and also you look at, say, both the strong links and the weak links, and I do it again. Yeah, and I can say, let's take Dharmendra as the starting point. Yeah, so we see that I can get partly from this person to this person through strong links or role relationships, or I can get through them through weak links like same address and same telephone, etc., etc. So when I rehydrate in code behind the scenes, just have a function where you say, well, first find shortest path, then use these generators to go and rehydrate the function with the original object. But let me just do a little demo here on the screen. Yeah, so I can say I choose address, email, and telephone, the predicates, and I can look at all the weak links, and I say, so how is he related through this person through weak links? And we find, oh, they were at the same address. And how is this guy linked to this company through weak links? And I find that this was related through a telephone number. And now let's rehydrate the strong links. So now I just do I choose perform role or has role, and I can do this. And I can say, how is this linked to this? Yeah, or how is this linked to this using only these roles? Or how was this linked to this? Yeah. So now I have a rehydrated graph. I could even throw away these strong links or throw away the weak links and start with Dharmendra again. And here I get the graph. Now because this graph gets a little bit too deep, I can actually toggle, the direction of the link, do it again. Yeah, so now you see how this person is linked to this person not only through role relationship but also through emails and telephone numbers. Yeah. Now obviously we can also do this completely automatic, but this is a really nice technique if you have to do huge graph search. We've used this technique also in telephone databases, and just imagine that you have every person has about 40 people that he regularly calls, and you make at least 10 phone calls a day. So if you want to know if Jans, ever called, say, Steve, then in a huge database with billions and billions of phone calls, it just completely explodes, and it's almost impossible to get the query done. So also there, we have this technique of creating a super graph where we make a summary of, did I ever call Steve in my life? But that's going to be a much smaller graph. Yeah, it only records if I ever called Steve. So then, when I do, say I do my shortest path, I find a link pretty quickly, yeah, in 1, 2, or 3 steps, and then I can rehydrate that shortest path by actually then looking at the actual phone calls made at a particular time, at a particular point. Yeah, and you can specify while rehydrating, what time frame you want it to look, or in what area, etc., etc. Okay, so let me go back to my presentation. So I leave these slides in my presentation so you can look at it later. Then with the same database, I can also do geospatial search. Yeah, so for example, actually let me just show you. It's more fun. Yeah, I can go here and do a query, find close address. So here's a prolog query that says select an entity 1 and an address 1, an entity 2 and an address 1, where based on a zip code, a European zip code, I find all the addresses that are all the entities that are within less than 10 meters. So in the underlying prolog code that I could show you, we use 10 meters. I have another function where I can actually specify the number of meters. But anyway, I can run the query, and I find a number of entities that actually live pretty close together, and I can select them and show them in the graph. So that was not smart. Let me throw this away. Okay, so now I have these guys here, and I can select the companies, the entities that they belong to. And I could say, are there any? So the only thing that we found so far is a few companies that are within 10 meters of each other. Yeah. But there's no, if I would look for the role relationship between them, I wouldn't find anything. But let me just look at other links that we might have between them. So I'm looking for weak links. And I could say, is there any link between these guys? No. Is there any weak link here? Yeah, there's a little bit of a weak link there. Yeah, so now I can look at this, and I can go a little bit deeper, find the relationships in between. Let me just remove this, and now if I start here, then what you can see is actually very interesting, because these two companies that are not linked to any role relationship do have a number of addresses that are different over time, and they share the telephone numbers that were different over time. Yeah, so for an analyst, this is very interesting to see where, I mean, you can imagine for analysts, it's kind of interesting to see that these companies somehow have a relationship, given that they shared addresses and telephone numbers over time. But the only thing they initially only knew was that they were close together. Yeah, and if you only look at the direct relationship, let me go back. Yeah, the only thing you see was one little line here, but this line hides a lot of complexity. Okay, so we'll go back to my presentation. Again, I leave these slides in here, so you can look at it later. And okay, then two more use cases where we use this approach. So one approach, and I'm going to talk about this probably in the near future, is the work that we do with the Montefiore hospital chain in New York, where we have about 2.7 million patients, and for each patient 10 years of electronic medical records and everything else that you can have. And so in that, what we do on that, so this data set is all stored in a big Cloudera stack on a cluster of machines. And so one thing that we wanted to know is how certain diseases were related. Yeah, and so what we've done is extract the data out of the database, apply R, compute the co-occurrence between any kind of disease that you might, that patients have in your data set, and then compute the odds ratio that one disease is related to another disease. Now, again, we started out with having a direct link, allergy to peanut related to dermatitis, but that's not that interesting. It's more interesting for the analyst to look at this and again have an object in the middle that specifies how strong a particular relation is. Like if you have allergy to peanuts in our database, then you have a 210 times higher, well, the co-occurrence that you find is 210 times higher than if it would be just chance. Yeah. So here we see a whole nice cluster around allergy to peanuts and everything that can happen. I'll just leave it at this because I will give a talk about this in January or February. Yeah. But again, we needed an object in the middle, but we still have the direct links that if you want to do very fast graph search. And finally, we had an investment banker, and I wanted to use CrunchBase to figure out, for example, if a particular investment company that normally invests in cloud-based application but hadn't done so in the last, but hadn't invested in a database-related product in the cloud for the last half year. I mean, there are questions like that. And again, you could say IBM invested in, say, the company Sherry Monolithics, but again, it was so much better to have an object in the middle where you can say, well, this was a venture, this was in the third quarter of 2000, and the amount that IBM put in, or the total amount that IBM put into this venture and that Storm Ventures put in this venture was $40 million, and the investee was Sherry Monolithics. And so this generated, again, a really interesting graph to see who invests in what. And again, this is a topic for another talk at a later time, but again, it was the same pattern. Yeah. So the summary is, yes, if you want to use direct links between objects because you intuitive you feel that's the best way, you can do it, but it usually is just too complicated. Yeah. Now people will say, can I do this with a regular property graph database? I say yes, you can, but it isn't. You don't use the property graph anymore. Yeah, if you use the approach that I talked about today. And my summary statement is that a mix of relationship objects and supergraphs allows you to, well, visualize relationships in a far more flexible manner. And the newest graph will have a feature where you actually can select what you want to see for these. So multiple attributes that you want to see for an in-between object. You can have very complex relationship. The query engine can actually, because they're just regular RDF or graph objects, the query engine can really deal with it very efficiently. And if you really want to do big graph search or social network analytics or shortest path, use the super graph and rehydrate later. So that was it. Any questions? We got one here. Yep. Oh, yeah, so one question is, I noticed you have a new tree layout. How do I do that? Okay, so there's actually several new things in Graph. Let me look at this. So let me go forward to where I was. Okay. So this is our new tree layout. So let me go back. I can say to the regular graph. I hit the letter R. Yeah. Notice when I move my mouse here, yeah, you see do tree layout from selected nodes. So if I click on this, it will do it. Yeah, I think we call this horizontally. I'm incredibly confused what we call horizontally and vertically in this case. I can go to visual graph options. I can go to tree layout, and if I unselect this, or I do a Ctrl-Alt-T, and I do the same little thing again here, I get the other layout going from left to right. Now, also some other new things in Graph, by the way. So here's for the tree layout. If you want to explore an object, yeah, without going to the tab view, you can just click here, and you get a number of things that you can choose from. So say you have the social security number or creation date. Yeah, I can click that. I right click, and I get the new features here. Very, very handy. What is another new feature? Oh yeah, and then this one here, say you selected a number of items. Sorry, let me go back. Say, here are the predicates that I've selected so far. Yeah, I hit the, let me Yeah, here I hit the letter P, which gives me the predicates that I've currently selected to use in discovering things on the screen. Well, once I have that, I can go to the little star here, and if I press that, then it will give me all the predicates for that particular set of, all the values for that particular set of predicates, and I can then reformat again. Okay, that was the graph question. New thing, what's this? You mentioned you work with Hadoop. Could you say more? Yeah, one thing we're working on at France here is to integrate AllegroGraph with the Hadoop stack. We actually recently got Cloudera certified. And as I said before, I'm probably going to talk about it in January or February, but what we do now is we take enormous amount of tuples and we store all the tuples in the Hadoop file system. Then we index all the tuples with AllegroGraph, and then we do parallel queries on the AllegroGraphs. And by the way, these AllegroGraphs run on the same machines that hold the Hadoop stack. That hold the on the same machines in the Hadoop cluster. I've been hearing about. I've been reading about MDM and graphs. Your thoughts? Yeah, well, actually, you can go to our website. We had a few articles about that, but I think it's actually what we've seen now is that big enterprises more and more start using ontologies to model all the information that they have. And then unlike with relational databases or other tools, you can actually explore the graph and visually inspect your entire master data management graph and actually even generate Sparkle queries or relational database queries completely on the fly just by looking at the big overall master data management schema. Last question. I saw Prolog in your presentation. There seems to be a lot of AI discussion lately. How does this fit in with AI? Well, I mean, yeah, we've been having Prolog in AllegroGraph for the last, I would say, 9 years. We had a Prolog interface before we even had a Sparkle. Prolog is one of the main languages of artificial intelligence, so you could say we've been doing that for a long time. But another new thing that we're doing a lot now is do machine learning on top of AllegroGraph, and again, I hope to talk about it in January, February. Okay, that was about it. Thank you for listening.